All right. Today I wanted to continue with our what is it? A disk of charge, right? We had a disk of charge, and we had a point of interest that was along that axis of symmetry, and we used some prior knowledge and some calculus to figure out what the electric field at that point should be. So now what we're going to talk about is okay, maybe that's the case when there's a reasonable distance and reasonable radius of the two objects. But what happens when our point of interest is extraordinarily close to this massive object? That's called the near field approximation. And then what happens when our point of interest is an extraordinarily long distance away from this object? So I'm going to go ahead and share my screen. As you can see up here on the left, I have recall that our sigma, our area charge density, was constant when we did these calculations, and we calculated the actual E field, and that's this thing right here. Okay, so now what we're interested in, this thing looks kind of complicated. Maybe we could simplify it down for certain cases. So I'm going to start with the easier of the two, the near field approximation. So when A is much, much smaller than R, what ends up happening here is, so let me write it down here. I'm just going to write it as the magnitude. We still have the constants out front. And of course, we still have the 1 minus. But if R is much, much larger than A, then this second term here is essentially equal to this, right? If A is much, much smaller than R, which is essentially equal to this. And when we have something much, much smaller being divided by something much, much larger, it's approximately 0. So this second term, using the near field approximation, goes to 0. And so what we're left with is the electric field strength is 2 pi Coulomb's constant times the area charge density. And then there's another way we can write this that's probably more common. Recall that Ke Coulomb's constant is equivalent to 1 over 4 pi times the permittivity of free space. So we'll go ahead and make this substitution. And that's going to end up canceling out the pi's and stuff. So what we're left with now is this expression here. You'll notice that several things cancel. The pi's cancel. 2 divided by 4 is 1/2. So what we end up with is that the near field approximation is sigma over 2 epsilon 0. All right. So this is the near field approximation. And this will pop up later in the semester using some different methods as well. All right, now on to the far more challenging one. This one's got a lot of twists and turns in it. So for the far field approximation, this is when A is much, much larger than R. And you might be tempted to use the same logic as we did last time. And you could do that. I just want to point that out. If A is much, much larger than R, then what you'd end up for this 1 minus term is you'd end up with A over this approximately the square root of A squared. That ends up being 1 minus A over A, which is of course just 0. So we went too far, right? We went so far out with that style of approximation that the E field went to 0, which is true. As you go to infinity, the E field goes to 0. But we're kind of looking for something a bit more interesting than that. This would be considered a trivial result. All right, so what I'm going to do now is I'm actually going to erase this near field approximation stuff because we're going to need the room. All right. So the first step in this long process of the far field approximation, I'm actually looking at notes because it's kind of a couple of strange steps. So firstly, I'm going to give myself a common denominator with these two inner terms. So of course the constants still remain. And if I give these things a common denominator, what I'll end up with is square root of a squared plus r squared minus a, all divided by, or I'm sorry, let's think here, because this needs to be over a. All right, so I'll times the left term by, well, actually, let's see here. Actually, what I'm going to do first is I'm going to pull the a out of, I'm going to pull the a out of the terms. That way I go back to this. Sorry about that delay. And so now that I've done that, now I'll get a common denominator. And I'm just going to do dot, dot, dot for this whole constant area. And what you end up with is you end up with the square root of a squared plus r squared minus a divided by a times the square root of a squared plus r squared. So you see I multiplied this term by a over a, so I didn't change it. I multiplied this term by square root of a squared plus r squared, which also didn't change it, right? Basically multiplying by 1 to find the common denominator. All right, so now at this point, this mess in here, one thing you'll probably start picking up as a trick, and maybe you already have, is that we don't really like this big old square root thing in the numerator. So why don't we multiply both top and bottom by the conjugate of that term, the real conjugate? So what that means is I'm going to multiply this whole thing by the square root of a squared plus r squared plus a. Then, of course, what I do to the top, I must also do to the bottom in order to keep the proportions proper. All right, so you'll see the magic of the conjugate. The only thing, so the conjugate is just, it's this term, but if there's a minus in between the two terms, we put a plus. If there's a plus between the two terms, we put a minus. So that's how we find the real conjugate. All right, so now I'm going to distribute the top, and that's going to give me a squared plus r squared, right? Square root of a squared plus r squared times square root of a squared plus r squared is just a squared plus r squared. And then here's the beauty of the conjugate is I end up with plus a square root a squared plus r squared. And then the third term is minus a square root a squared plus r squared. So those two middle terms in the FOIL process cancel. And then minus a times a is just minus a squared. Then I have this pretty crazy denominator. But we'll be able to get rid of that eventually. All right, so you may notice that in the numerator here, the a squared minus a squared cancels out. And so this thing just becomes r squared over all this jazz. And we're going to go ahead and figure out how to cancel a lot of this stuff out. And how we're going to go ahead and do that is we're going to say that, okay, so since r is much, much smaller than a, I'm going to go ahead and change this denominator to say that this is a times, instead of a squared plus r squared under the root, because r is much, much smaller than a, I'll just write it as a square root of a squared. And then for this term right here, I'm going to do the same thing, right? So a squared is much, much larger than r squared. Therefore, this just ends up being the square root of a squared plus a. And so we have this less complex denominator using our approximation. And so now I'm going to write it back in the electric field strength formula with these constants back in there. And now what I'm left with is, let's see, r squared over, and with some simplifications, right? square root of a squared is just a. So I end up with a squared times 2a. I'm just going to write that now as 2a cubed. All right, and now it's time to do some simplifications. So we see that some of the a's cancel out. So there's still this r squared in the numerator, but and actually, yeah, so now we have 2a squared in the denominator, right? Because a cancels with a cubed and leaves a squared there. All right, and the 2's cancel. So it's looking even nicer. And now is the final step to kind of produce something that looks interesting and familiar to us, which is the whole reason that I've decided I wanted to do this problem. Recall that sigma, the charge area density, is equal to the total charge of the object Q divided by the total area of the object, which in this case is pi big R squared. And so we're going to go ahead and plug that in for sigma. And what we'll see is that E is now equal to pi ke R squared over a squared, right, times sigma, which is total charge of the object divided by pi R squared. And we see some nice canceling going on here. The R squared cancels the R squared. Pi cancels with the pi. And what we're left with is the electric field strength for the far field approximation is Coulomb's constant times Q divided by a squared. And you may recognize this because if we go ahead and just say, let's just call a little r, and we'll call big Q little q. And what we end up with is E equals Coulomb's constant times Q divided by r squared, right? This is the electric field equation that we learned in the second video. And so what's cool is with the far field approximation, right? If you go too far out, the E field is just approximately 0. But if you go sufficiently far out, but not so far that E goes to 0, this charged disk will actually appear like a point charge, right? So in other words, like imagine you're standing at this point of interest and looking towards the disk. So when you're close, it's going to look like this. You start backing away though, it gets smaller and smaller and smaller, and pretty soon it's just behaving like a point charge, and out pops this equation that we are now used to. So this is the far field equation for this. And what you'll see is these things pretty much pop out of any shape that you can zoom out from sufficiently, or any shape that you can zoom into sufficiently. You'll get some sort of approximation like this. All right, hopefully that wasn't too much of a run through the mud. I know the second one is tricky. Took me a while to rework it out, so don't worry too much about it. It's more about the interest of this electric field equation for a particle popping out of this disk equation. All right, I hope that was interesting to you, and I hope to see you next video.